this video we're going to go over the product kinetics, and namely the Luden-King-Pyre equation. So this equation is used to calculate variables in mixed kinetics, and mixed kinetics covers the products formed from growth and non-growth related cell activities. We have the equation here, where Rp is the volumetric production formation rate, Rx is the volumetric biomass growth rate, also shown here, and X is the biomass concentration. These two equations were introduced in the growth kinetics video. So, if we move on to the example. So we have a microorganism is cultured in a 6 meters cubed bioreactor. The initial inoculum concentration is 2.796, and the inoculum concentration at the end of the growth phase is 4.935. The specific growth rate is 0.36. There is no lag phase and the batch stopped at the end of the growth phase. Calculate the amount of product formed. So if we write down all the variables we're given, we have specific growth rate at 0.36 and the inoculum concentration goes from 2.796 to 4.935 kilograms per meters cubed. So now that we've got that, we can use some of the equations from growth kinetics to work out the amount of product that's formed. So if we start off with this equation, x equals the initial e to the specific growth rate multiplied by time. This was covered in the previous growth kinetics video as well. And we can rearrange to find t. To find t, we need to use the natural logarithm of a specific growth rate. So I've just rearranged it. If you divide both sides by the initial and then take the natural logarithm of both sides and then divide by specific growth rate, we can get t by itself. So we need to find the time which this batch takes place. So if we plug in all of our variables, which we have the end divided by the initial, all divided by specific growth rate. That gives us 1.578, and that'll be in hours. So now that we've got that, we can start manipulating this equation using these. So we have Rp equals 2.7 in the place of alpha, 2.7 Rx plus 0.32x. Now we know that Rx, so the volumetric biomass growth rate, is equal to the specific growth rate multiplied by the biomass concentration. And we also know that the biomass concentration is equal to the initial biomass concentration to the exponential of the specific biomass of the specific growth rate and the time, which is what we used before. So we can substitute these into our equation. So if we substitute Rx, we have Rp equals 2.7 plus 0.32x, and then what we can do is we can factorize, because now we have an x on both of them. So if we keep going, and then we substitute in the x for here, equals 2.7, and we have, so now that we have this, if we look more clearly at what Rp is the volumetric production formation rate. So it has units of kilograms because it's a volumetric production, then it's per volume rate, as in per unit time, so per hour. So it's actually the volume of product formed per hour, in other words. So it's similar to dP over dt, the amount of product formed per unit time. So we can use this differential to do an integration. So if we rewrite dP over dt as Rp, we can integrate between this amount of product formed and the initial when there's no product. So that equals, and on the right hand side, if we integrate between time t and 0, so we have 2.7 plus 0.32, and that's multiplied by the initial, which we know is 2.796, and that's between the integral, because we have e to the specific growth rate times t, e to the, we know this is 0.36 from here, and t is 1.578 dt. So now if we put all those numbers in a calculator or manually do the integration, we should be able to get the product formed. So P equals, so we have 2.7 multiplied by 0.36 plus 0.32, and that's all multiplied by 2.796. 3.612432 multiplied by, now the integral of this, so when we put t in, sorry, that should be a t, because the nt is 1.578, the initial time is 0, so when we have 0 on top, we have e to the power of 0, and e to the power of 0 is 1, anything to the power of 0 is 1. So what we get is e to the t minus 1. So then we can put in our value of t, which is 1.578. So we get p equals this multiplied by e to the power of 0.36 multiplied by 1.578 minus 1. That gives us 2.763 kilograms per meter cubed, because that's the volume concentration of product per cubic meter. So because it mentioned in the question we have a 6 meter cube bioreactor, to calculate the total number of product formed, we would multiply this by 6. So the actual number of product formed is 16.58 kilograms within that batch. And that's it.